We kicked its ass. Oh, excuse me, arse. So
It was a fight.
how you doing?
Good. How are you doing, Bill?
So you might notice this is not Ben. This is Mike. Ben couldn't be here today, but we are going to talk about. Mike has been on an exploration of this book you see here, High Speed Digital Design by Howard Johnson and Martin Graham. And basically, you've not been. You take what you read and then you want to see it yourself. Is that a fair?
So it is, because every time this is my experience, I'll read some of this stuff and I will think that I understand it.
Right,
and then I'll go build something and I find out that I didn't understand it or I understood like 80% of it. And then I'll have to.
Is it that you didn't understand it, or that you got different results and so you got it didn't work the way you thought it? You didn't get the results you thought you would, but you still think you understand the way it works.
Yeah, I think I got like the basics of what they're talking about in that book. But then there's like, maybe it's the subtleties of the little things, like when you actually go to measure something. So it's fair to say that it's not fair to say that I completely misunderstand everything I read in there, but it's always instructive to go build it, and then you like see the real thing and you're like, here's like an extra aspect that I didn't think about. Or you fail to build the real thing correctly and you figure out like, well, what did I do wrong when I was making it, you know?
Oh, then that's cool, because that's how I learned, right?
Yeah.
I didn't learn because stuff worked. I learned because stuff didn't, right?
Yes.
And rather than understand the math behind something, which would tell me the proper answer, I'd fix 100 things and learn all the broken answers, and it typically leaves the only correct answer.
Yes.
So yeah. And we're going to talk about something in there. I saw your one reflection that you cured with not cured, but treated with a series resistor. And there's an ugly truth in the series resistor usage. And we'll have to sanity check this by Ben next week too, in case I'm getting some of this wrong, because he keeps me honest.
Yeah.
So
yeah,
did you want to go ahead?
Maybe the first thing we could talk about is so one of the things I made was basically all the ways that they talk about in this book on how to terminate transmission lines, basically. And you mentioned series. That's one of the many ways. So I made a PCB that basically has all the ways. And this is an example where when we look at this, there's the PCB there. So I will share a different screen that's going to show like.
Yeah, do that.
I'm going to share so I have the wrong thing being shared right now. Let me share this other thing here. So let's see. Pardon me while I try to figure out Skype. I'm going to share this one here. And I don't think you have to do anything, Bill. It'll just show up.
I shouldn't. And there it goes.
Okay,
isn't it amazing when technology doesn't get
you're
pissed
just
and kick our ass right on back?
So what that screen there is showing the schematic of what I made. Man, it might be hard to read some of that stuff.
Yeah, I'm about to expand it. There you go.
Oh, okay, great. Yeah. So what I did, and Bill, you can tell me if there's anything silly in this, but this is just my way of going at it, was I basically took a hex inverter and just kind of like daisy chained from one line to the next, to the next, to the next. And for each one, I put in a different kind of termination, if you will. And
where did you get these terminations? Are these out of the book?
They're in this book, and there's also a book by Eric Bogatin that has terminations. And what I found interesting is like even the names that you use for them changes from author to author.
Yes.
Or when I'm talking to you, Bill, you'll have a name for it that matches one of the two, and I find out it's not what I was thinking it was, you know. So it's maybe there's just a nomenclature thing, like what do you name these things?
Right.
But
go ahead.
The schematic makes it clear. It's like this is what I mean when I say this kind of termination.
Right. And so what you're calling in parallel, well, let's back up a little bit and talk about transmission lines.
Okay. Yeah.
And a transmission line happens whether we want it to or not when we try and send something high speed down a PC trace. And on a good day, there's a ground plane for the return current to match it, and we get a more or less controlled impedance, which is the AC resistance along the path. And on a bad day, it's just a signal wiggling its way through other signals and inconsistent grounds. And so the impedance you know, the way that field as it propagates, it sees things get wide and then skinny and wide, ground and no ground, ground, and reflections occur. That signal doesn't transfer that power that it left the gate, doesn't all arrive at the destination.
Yeah.
And then another thing that can happen is when it gets to the destination, if the destination doesn't absorb the exact amount of power, if I give it 50 units and there's 40 units down here, 10 units will go back the other way. Right? Does that sound right?
Yeah, and even so, even my understanding as of like a year and a half ago was nowhere near this kind of stuff. And I knew I think you pointed out to me, or I read in various places, like the idea that, at high frequencies, the return current basically goes underneath the trace. It follows
the path of least impedance, not least resistance.
Yes. And I even misunderstood what that meant, because I thought, in my mind, mentally, I thought, there's a wave that propagates down the line, and then I thought the return propagates back down underneath.
Like two delays, instead of one delay with it, right.
Instead of like the tractor or the
a front wave, yeah.
So I even had an incorrect mental model, and you had showed me a picture that, like, once you showed me like this animation of what it actually looks like, then the light bulb went off in my head. I was like, there's this wave of all of it kind of just, and it makes sense then, obviously, in hindsight, of course. Like, it's not two delays.
Right.
But
then, you know, what gets tricky is when you have a differential pair.
Okay.
And you think of it as going down the positive and coming back the negative. That's not how it propagates in my world. It propagates where let's call it the positive signal and the negative signal, they're still coupling the ground. They're just doing it at the same time. It's not going down and around the horn and coming back. Okay, they're both going to the receiver at the same time. Oh, look at that 3D House of Thievian. So I don't know the real correct answer that somebody like Eric Bogatin would give. For sure to a differential signal propagation, but I think of it as two 50 ohm propagations, not that share a 100 ohm component between them, but it's not down and back as you see when you look at a circuit. Now in DC, it looks like it goes down and back. It does to me. You know, if it were current flow, electrons, it would come. There'd be a circle that path takes.
Yes, in DC, and that's what my mental model was heavily influenced by DC. Yeah.
DC and analog, you know, and I used to do instrumentation, and we had differential front ends, and there has to be a loop of current flow or no current flows, right, at low frequencies. So so that's a transmission line. Go ahead.
Yeah. So like a year or two ago, I was doing the things on breadboards, right? I had no clue what transmission lines were. I just, like, maybe the way things were done in the 60s, as long as you connected it together, you're good.
Right.
Point to point, whatever you want to call that, wire wrap it, you're good to go. So essentially, I guess that the idea is, if your board gets to be large enough, or if the frequencies get to be high enough so that the electrical length becomes important, then you start to have to worry about, like you said, these reflections could cause issues. Like on the C128, which we'll talk about later. I guess there's another. Your reflection on the series one I want to talk about, because there's a dirty truth in there. But you just happened to mention wire wrap. Yeah.
And I'll tell you that wire wrap actually is not bad. It's still, especially if you end up with a good ground, but even without a good ground, a well-done wire wrap where we take the pieces of wire, put them on each socket and go straight to a socket. Because we can go straight there, we don't have a lot of reflections and corners, and if you don't bundle the wires together, you even spread them out, you don't get a lot of crosstalk. We've gone amazingly fast on wire wraps. And we used to still ground grid and stuff. We would take tinned wire, and on the top of the board, we would have a grid of ground, and on the bottom, we would have a grid of plus, or vice versa. And then we would lay those wire wrap wires right down on the grid, so it sees grounds going by it as it travels. But we actually, and ECL used to be, I've seen ECL stuff wire wrapped.
The thing that I remember that was interesting about wire wrap is that it's arguably better than solder in terms of the connection on the end. Because when you like tightly wrap that wire around the pin, it actually like welds itself to the pin. Like I was reading that, like with wire wrap,
when done correct, it's like 2.5 wraps of insulation followed by 3 wraps of knot in the corners of the post cut into the wire.
Yeah.
And that cuts through the oxide and everything. It's actually not a bad joint when it's done perfect, really well.
Yeah, I was reading that's, or I don't know if it still is, but it was like the preferred way to do like aerospace applications over just using solder, because wire wrap is better in that sense. It's
right, or let's say bad solder or a bad PC board.
Yeah.
And back then they had single-sided boards, and they were called PWBs and stuff. So so Chris just asked on on YouTube if a differential pair, the signal actually propagates between the conductors, right? Not in my head. The signal propagates between each conductor and its return path. They just happen to travel in parallel, and one's going high at the same time as one's going low. So you're propagating a high signal and a low signal, but that doesn't mean that the AC current's flowing between them in my world. Now, I could be wrong, but it's me to ground for going high and me to ground for going low, and they happen to share then an impedance relationship between them. If it's 50 ohms to ground, 50 ohms to ground, we design it to be 100 ohms between each other.
Okay.
So just to kind of back up a little bit. Didn't mean to do that, but solve the question. All right, so where were we?
So this PCB that I made was basically an exploration into trying to make all the terminations that I could find in these books, and the PCB, I don't know if you can see it on the one that Bill has there. The traces are really long. Just I tried to exaggerate the effects of electrical length, if you will. So yeah, that's good. So it's like
now you did this in Proteus, right?
I did, yeah. So I didn't actually have to do all the little wavy things myself.
Then that's what I was going to ask. So they have so you set the circuit length, and then did you give it parameters for how tight to make the little S curves, or did it just default to something?
You can mess with that, but I think I went with the defaults. Yeah, you can mess with it.
Right. Yeah. Oh, the defaults aren't bad. It's just on some you can't change them, and on some you can change too much about them and really screw yourself up.
Okay.
Altium, you can change everything about the delay lines, including how sharp they are, whether they're rounded, squared, or whatnot. So what's the length of your lines here?
Oh, I think it says on the PCB. I think I wrote it
24 inches?
Yeah, it's like 24 inches long, right? I can't read.
Right, not bad for a 6-inch board, 4-inch board, whatever this is.
Those are some crazy long traces.
Do you happen to remember how fast on a standard PC board? Do you remember how far you get in a nanosecond?
Yes. Okay. So, light and free space is what, a foot per nanosecond, right? But on a PCB, it's half of that. Is that right? 6 inches.
I didn't remember. I didn't know the foot per second. I remember it's 6 inches per nanosecond on a PCB that typically has a velocity factor. I would have said 0.7, not 0.5, and the velocity factor is the ratio of how fast you can go versus, or of light in a vacuum versus light in a medium like this.
So these are like 24 inches long. so
I would expect them to be 4 nanoseconds.
Yes. Yeah.
So let's test that later. Then when we look at your drawing these things.
Yes. Yeah.
Now, yeah, so I see some real, there's some cool stuff here, dude.
So this is me just exploring and trying to try them. So what I did was, and there's some interesting stuff that I found that I think, especially in what's called the parallel, we'll get to that surprised me. And it makes me think maybe I was doing things wrong, And this is the way I learn, just try it, fail, figure out what you're doing wrong.
Right.
So we could maybe go through them one by one and talk about each termination style.
Yeah, pick one.
So
start the top
and go around clockwise or counterclockwise. So the very first.
We'll start with the simplest one. Do you have an unterminated? Oh, yeah. Let's start with the non-terminated one.
That's a good point. Yeah, the one in the lower right is non-terminated. So if you look at if you look at those traces in that picture there, the one there it says no termination. And what you can kind of see is that there's like a little bump at the top of that, or it's kind of like it looks like an
overshoot.
Yeah.
It's overshoot. It is overshoot. Absolutely.
And if you look at how the duration of that, I bet that's around that 4 nanosecond thing we were just mentioning. I can't see the graticules on those pictures anymore. They're too small.
Right. So we're going to have to just estimate. So first it overshoots, and then it kind of rings back. Actually, they can't see my mouse, so you might use your mouse on it and show it overshoots, and then it undershoots a little bit, and then it levels out, and then it does the same on the downward leg. It really undershoots.
Yeah. So this is it's basically the signal going down to the end, banging off the end of that pin, and then coming back.
Right.
Just adding up or subtracting whatever it's going to do until it decays and is gone.
Right. Now, I'll tell you, the overshoot isn't as big a thing here on the high going, but in real life, it's the negative going one where it undershoots. If you undershoot more than like 0.3, 0.5 volts, you can actually screw up the circuit. It becomes an illegal logic level for purposes of calculating its delay. In other words, a propagation delay. Hey, I got it to you, but I went negative. Well, you can't say you got it to me yet. It has to be a legal voltage value. And a legal voltage value is like ground minus 0.3 up to, 0.8 volts is a valid low. Going below 0.3, negative 0.3 volts is not a legal low voltage. And before it conducts a diode and the transistors go wonky on you and stuff.
Like the protection diodes kick in and...
Or parasitic diodes. Yeah, actually, what happens is the way the transistors sit on the substrate, they're a diode in normal operation, but suddenly, you flip it over and it can go into conduction. It actually can start to make JFETs and things like that out of them too.
So for me, the next simplest one on this list is if you would say, okay, let's just put a 50 ohm termination at the end of the line, and that's in the upper right. So if maybe you might have to scroll it out a little bit to see that. But that's like, if you say, I want to terminate the line, that's the one I think is labeled parallel, which is, I find an odd name for it.
and that's not what I call a parallel termination, but it is a parallel termination. I just call that a terminated line.
Yeah,
right?
Okay. I'm with that too, because I wouldn't have called that parallel.
Right. Well, we used to use what we used to call parallel termination is what you've called Thievian, and we used to say it's a Thievian thing, but it's a parallel termination. Okay. But you're actually correct in the way you've drawn this out. Is my memory here?
Oh yeah, I looked them up in the books just to be sure.
Right. And I'm not going to argue with the books. Right.
Don't argue with Bogatin or Howard Johnson. Yeah.
Yeah. Right.
So the thing that I found surprising about that is I just naively slapped a 50 ohm resistor on the end of that. And the lines, I think, are 50 ohm transmission lines. And the thing that I found surprising is that transistor seems to be loading down the line. So that's a thing that I just
it's supposed
learned.
to load down 50% of it's supposed to go into the load. It forms a voltage divider between the 50 ohm impedance of the transmission line and the load. And so when we want to do like coaxial video amplifiers, we have to put twice the voltage we want onto the coax. And when it gets to the end, it becomes a voltage divider into the 75 ohm load, or, if it's a 75 ohm coax. And so we get our original voltage back, but we started with twice the voltage, and we end up with a voltage splitter in video term.
Okay. So I still don't know what the right thing to do is there. And you would probably argue no one ever even does it this way anyways. But it's like, it's a natural thing to do. You're like, let me just terminate the end of the line.
Oh, we do it all the time in video. Absolutely. This is how we get video down a coax to where it arrives nice and crisp and it looks like the signal. We just had to start with a 2x amplifier. And you did that yourself. Didn't you make a video buffer at one time? You showed me something like that.
Oh, yeah, there was.
Because I showed you mine. You showed me yours, I showed you mine.
I was doing an op amp to try to drive enough current into a coax line. Yeah.
And you used a current mode op amp, right? You didn't use a standard voltage op amp. You used something that is a video buffer meant to drive coax cables.
It was a special op amp for that. Yeah.
Right. It was a current-based op amp.
Yeah, and to be honest, to this day, I still don't understand why I would need to actually do that if I had a good enough, here's where this is the trouble I have mentally. The thing that I don't get is if I have a 50 ohm line and I can drive it, like these are 50 ohm lines right here, right? I can drive them. Why would I need a special op amp to drive a coax? Is it because it's got a lot of capacitance in it or something?
Yes, it is. Op amps hate capacitance. They just hate it with a passion, and they'll break into oscillation typically because it introduces a pole in the feedback, right? Because most op amps are used with negative feedback. If you're going, hey, I'm going along good. Whoa, hey, I see this 1,000 puff. That's what we used to call picofarad in the old days. A puff load. Suddenly now that feedback is behind in time because it's an RC network with the R. Think of R now and C. R represents the amount of current you can pump into the C. It's limited by R.
Okay.
So that ability to supply current ends up to be a pole. The less current you can supply, the higher resistance it looks like, the more it looks like a bigger resistor and a capacitor, and that looks like a bigger RC delay coming back in the op amp.
Okay. So these op amps have just a lot of sophisticated circuitry in them to try to deal with.
Yes, they pump it. Yes, that's the way. As a matter of fact, the one I used, you can't just pick any old feedback resistor. Mine was tuned for, I forget the number on the op amp, but it was tuned for 352 ohms feedback, and not even a lot, but the feedback resistor was 352 ohms to drive a coax. So it was optimized for that. So yes, it's a special circuit to drive coaxes.
That's part of what I like
somebody
about
mentioned that a coil of coaxes makes a wonderful delay line. Yeah. Hey, we got Alan is with us. He's going to give me the right thing. There's usually form between the output impedance and the termination. Output impedance, and yes, it's the output impedance, and to me, the output impedance matches the transmission line impedance. So I was mentally making a shortcut that's probably a faux pas here. So, by the way, Alan Wolk, who has just joined us, W2 AEW, will be our special guest next week, and he's going to turn my ramblings of a madman into actual fact and stuff like Ben what Ben does for me here.
Wow. Alan Wolke is on the line, man.
Yes.
Awesome.
So it looks like, so he said, an infinitely long transmission line looks like a resistive impedance. Line's characteristic impedance. Yes, absolutely.
Okay.
So, yeah. But Alan, it's still a voltage divider, right? Oh, yeah. He said the divider is usually formed between the output impedance and the termination. So, yeah.
Okay.
So
so
all right. Well, I got to watch what I say now that there's experts on the line here.
So that was my simple.
Wolke. he said to pronounce his name.
Now I'm afraid to speak in front of Wolke. Yeah.
Now we're done. We're done for the.
Yeah, it's a great way. So anyway, so the next, so that's maybe a naive way to terminate a line is just slap a 50 ohm resistor on the end of it, and then evidently, if you do that though. My understanding is if you do that, then if your signal stays high for a long period of time, then you're wasting a lot of current flowing through that resistor. If your signal is at ground, then there's no current flowing.
Right.
So
and what I was going to say, and one of the dirty secrets of TTL is we were always throwing away half the power because the voltage high is 2.4 volts. Well, we go all the way to 5 half the time. And so we're throwing away the 2.5. That all becomes noise margin, and we have a noise margin of half VCC. Meanwhile, down near ground, we only have a noise margin of 0.4 volts. So TTL was always unbalanced. And so we always knew that we would end up with like 3 volts. Even in the old days, we knew we were throwing away voltage and consequently throwing away power. And so now that we're on 3 volts and then 1.8, all that is great for getting rid of power, excessive power dissipation.
So I think the answer to this, the lack of symmetry in that little design, is that thing that's in the upper left. It has two 100 ohm resistors, one going up and one going down.
So what's the impedance of 2 100 ohm resistors, one going to VCC and one going to ground?
Yeah, I still find it weird, but it's 50 ohms. But
it's 50 ohms, yeah.
But I find it weird. It's like how
I had to learn that too.
That's the Thevenin. That guy figured that stuff out 100 years ago. And yeah, I still find it challenging, but yes, yeah. What I find
is that how you pronounce it, Thevenin? I always pronounced it Thevian, but then I used to say cement too.
I don't know. We could go poll all the people in New Jersey. How do you say Thevenin? Yeah, I'm sure your way is just as good as anyone else there.
Right.
So that's what that one is. Oh, and that one also has the same curve. It's also loading the line down in the same way.
It's loading the line down.
It's like it looks the same, but it's not. You're not seeing anything bouncing back and forth. It's pretty good at like preventing reflections and overshoot and that kind of stuff. So
right. Now we need to mention that part of the issue here is the input impedance that of the chip. Is very high. Very high.
Yes.
This is a CMOS input. If this chip had a 50 ohm impedance of its own, we wouldn't need an external terminator. We would couple all that power directly to the chip. The problem is we get to the end of the line, there's a high impedance and it bounces off there if there's nothing to absorb that power.
Yes. So the last one, well, the very last one we'll talk about is the one that I think that everyone does. It's the series one. But then right before that is another more complicated one, which is kind of in the middle right. And it involves a resistor and a capacitor. What is the name of that one?
That's just an RC. I used to call them snubbers. Yeah.
Okay. And man, I'd have to read this part of the book again, but my understanding is that it's just better for like power consumption kind of ideas. That's my only memory of this thing.
That's an excellent way to look at that, and being a guy that's not math based, but that was actually it. Is we took the bite off the edge, and yet at the end of the day, the DC current, and this is real important on backplanes where you maybe have 50 signals. 50 signals into 50 ohm resistors is a lot of power being thrown away. So the RC, I've seen that used, and I've seen that fix more things than I can count years ago. But yeah. Okay, so then the very last one is one that I honestly find kind of weird. You put a resistor in series at the beginning of the trace. And that's my holy holy circuit. That's the only reason I ever got anything to work in the old days.
So the weird thing about this one is if you zoom in, Bill, the two traces on the left, you have to kind of understand what's happening to the traces when you do this. Actually, like it's the two traces in the lower left. And as a matter of fact, I have it going on my oscilloscope, but the weird thing about this one is if you measure the voltage curve at the beginning of that line, what you'll see is you'll get half the voltage initially. And on the far end, when that half voltage, let's see if I can describe this properly. As that half voltage kind of goes down to the far end, it reflects off the far end because the far end is not terminated. It's a high impedance ending there.
Right.
And because of that, it reflects and it brings it up to full voltage right immediately, right when it hits it. And then that full voltage thing comes back down the way, and that's where you see. See if I don't butcher this explanation, but if you look at the picture in the lower left that shows the step kind of pattern.
Right.
When you're measuring the near, you see that effect. You see like the half voltage for a little step for what we think might be about 4 nanoseconds. And then when the reflection comes back, then it goes all the way up to the top. And,
right.
And
it absorbs the reflection, as Alan just mentioned. Yeah.
Yes. That 50 ohm thing there basically, I guess, forms a voltage divider. It effectively like absorbs that 50 ohm.
Otherwise, in theory, it might bounce back and forth forever, or at least losing, because there's no such thing as perpetual motion. It would bounce back and forth and dampen out. Now, we used to, when driving DRAMs arrays, which were very high capacitance, we couldn't use 47 ohms. It would give us too much of an RC. So we would do what we always do, which is a compromise. And, and we would empirically find that something like 22 ohms was the sweet spot for us, where it absorbed enough of the reflection that we got what we needed out of it without adding a huge RC delay to the circuit. Okay.
And what I want to say there, too, about that subject is if you look on the picture, I put a 43 ohm resistor.
Right.
Because I think I knew that, like, the chip itself, the pin, might have some resistance in it or some impedance.
It does. It consumes some current, yes.
And I think, so maybe that's like you said.
And it's a capacitor.
Yeah, So you have to kind of like, if you look at the traces that I measured, I didn't quite nail it with that 43 ohm resistor. You can see a little bit of a secondary step there where it didn't quite, it's not like perfect.
Right.
And maybe that's where you have to experiment.
Well, in the way I've designed high-speed, computer stuff, I've never gotten perfect. I never did perfect transmission lines between every single point in a design. LVDS, yes, I go for transmission lines. For a 1 gig signal, yes, I go for a transmission line. But for the odds and ends, all the signals going everywhere, you use what works most of the time. Good enough. You get it above the high threshold, and if it reflects a little bit after that, it's par for the course.
This might be a good segue to the next half of what I wanted to talk about, which is if you're driving something into a pin, how do you measure its input impedance? What if you want to know what it is?
Oh, this would be a great question to run by Alan since he's with us. So can you bring up your vector analyzer?
Yes, I will. First, I'll bring
print?
up a picture of the setup that we're using to measure this first.
Okay.
Let's see if I can do this again. All right, settings.
So I'll explain real quick. The question we had on our Discord channel is can we observe the impedance of a gate, of a logic input on a gate, and does it change when it's in a logic low state or a logic high state? And so I just happen to say, why not put a bias T in front of it and give it a logic low and a logic high?
Yes. And I've still to this day, I find that pretty clever. I'm like, wow. It's like you must have had to sleep to figure out that one, because that's like...
I've never thought of it for a digital circuit before, but I didn't know a reason it wouldn't work. And so maybe somebody can comment on whether that's valid or not. But that's what we did. We said we want to, off to the left is a piece of test equipment. They can't see my mouse, unfortunately.
Okay.
And off to the right is the receiver. And then you fed it the voltage coming in the bottom here of the T, right?
Yeah. So yes, the DC is either the high or the low. And it's kind of like, the interesting thing here is like, we want to measure the impedance of that pin, right?
Right.
And maybe one way to think about this is, and you had mentioned just doing it with the VNA, and at first I was like, how would you do that?
That's not a logic level. Yeah. What's the chip going to do to 1 volt peak to peak or whatever comes out of this?
It took me like a couple of hours to figure out what you were talking about when you suggested this bias T idea, and I'm like, what is Bill saying here? And then finally I'm like, oh, this is just like if you want to measure the impedance of an antenna, in a sense. Like you basically measure the S11 using a VNA, and you're seeing like, if I send this signal down the line to an antenna, does it go out the antenna or does it reflect back off? And that's what S11 is about, is reflections back off the antenna.
Right. Ultimately, it helps you determine your standing wave ratio, which is the ratio behind what you sent and what you got back.
And my VNA is fancy enough where it'll just tell you the impedance. You don't have to.
Okay.
I think your VNA might be fancier than mine, but you have to go do spreadsheet stuff to figure out the impedance.
Yeah, there are some things I've seen other VNAs do that I couldn't do with mine. But next week we're going to maybe see a VNA. I know we're going to see a spectrum analyzer from Alan Wolke, but maybe we can even get him to show a VNA.
So here's the VNA.
Oh, hey, did you happen to do the calibration with the bias T in place?
Yes, I did.
Very good.
Here's my setup up close. This is the VNA that I'm using, but it's it's a little USB based VNA.
Right.
And yeah, I basically did it at this measurement plane here. I took this thing off that I was measuring, and I put my my short and open and load there to kind of calibrate out the effects of this mini circuit's bias T part here.
Now yours is a USB-based VNA, right? It draws it on the screen and right. Yeah. And so here's mine. Mine's a Tektronix TTR506A.
Oh, I'll trade you if you want. You can have mine. I think I prefer yours. So
go ahead.
So the idea here is that we're just using this to measure the impedance of that chip to see if stuff's reflecting off of that pin. or being absorbed in it. And you can kind of get a sense of like, what is the input impedance on that pin? And you can, furthermore, which is the cool part, is you can see how it changes if the driving voltage on that pin is low or high. This is the theory that we have. And
so were you driving it from a DC source, or were you driving it from an oscillating source? Did you do it once with voltage high or once with voltage low, or what did you do?
I have a picture of that too. I'll show you what the thing measured. Let's see. And you'll see that my fancy VNA can tell you the impedance without you having to do any math. Let's see. So I'll stop sharing that screen. Okay. So tell me if you see it. We're just gonna, there it goes.
Yep.
Okay. So what we're looking at here is basically a sweep over frequency of the S11 being measured by this VNA.
All right.
And it's not just like showing it in terms of like VSWR. It's actually showing you the impedance. In
terms of impedance.
Yeah, that it calculates from that. So you can kind of see that at lower frequencies that has a higher impedance. Because I think we at least if you said, hey, Mike, explain this, why is this curve shaped this way? I want to say that the input pin on that chip is capacitive. It's slightly capacitive. So as you go up in frequency, the impedance drops. That would be my explanation of this. The square shapes that you're seeing, like the up and down, you can kind of see that. That's what's going on there is as it's sweeping, which this VNA is kind of slow. It takes about say like 8 seconds to do this sweep. As it's doing that sweep, I have my signal generator hooked up to that DC port on the bias T, and it's basically flipping between 0 volts and 5 volts. So that was my attempt to try to like.
So you could have done this in 2 sweeps, right? You could have done this in a sweep where the bias T had a voltage input low or ground in it, and then done it a second time with voltage input high on it, or plus 5 or VCC or something.
Yes. And at some point I convinced myself that the tops of that curve is when the voltage is high. So the impedance is high when the voltage is high, and the impedance is lower when the voltage is low. And I don't think I could explain that. But that's what I convinced myself that I was measuring. Right. Is what kind of receiver, what chip did you drive into this? Oh, okay. That is it's an LS chip of some sort. Let's see. It's an LS. Okay. Yep. So when it's high, you're driving directly into the base of a transistor. God, I can't remember. But yeah, I would expect the current to be different on input low versus input high. And that would look like 2 different values of resistance, 2 different values of capacitance, I would think. Okay. So let's see what the... Now, do you have a Smith chart of this? Oh, man, I do. I think I did. Let me go look in Discord real quick. Yes, because I remember the shape of it did match up with that idea of it being slightly... That being capacitive? Yes. All right. That's a cool picture because since Alan Wolke is on the line, he could tell us all about how to read Smith charts. Well, we could do an entire show on that. I'm sure. I was going to have like Ben or Alan help with that one someday. Okay, so I learned this from Alan. Let's see if I can get this right. You crash down for capacitance, and you elevate up for inductance. Yeah, I've forgotten when which of the 4. Yeah. Because I used to think of it as clockwise and counterclockwise, and then I realized they both start with C, so you can't use that for. Okay, so I may describe verbally what I remember saying, because I'm not finding the picture that I made of it. But in a Smith chart, this pin, like the data that you collect here, is largely over in the right hand part of the Smith chart. It's over. It's near the open. Right. Okay. I remember seeing it, and it wasn't a big loop either. It was pretty resistive. So let's see. So Smith chart basics in the center would be perfectly 50 ohms, or the normal Z sub 0.
Normalized. Yeah.
And then on the way I remember is the left-hand side is short and the right-hand side is open. The two edges of that circle, the two boundaries of that circle. This one was over here on the right-hand side. The input pin looked like it was over there in the open side. It's as if the input pin wasn't even there. You know, it's just an open, high impedance.
Right.
But as the frequency went up, you would see the Smith chart trace would go down slightly, away from that open. So it was like a slightly capacitive open.
Right. And that's what Alan just reconfirmed, is capacitive is down and inductive is up. Yeah. Or as you said, crash for
down.
capacitive.
Yeah.
Okay.
So that's
all right.
Yeah,
what'd we end up with here? We ended up finding out that the chip is nowhere near 50 ohms by itself.
Oh, right. Yeah. So what is it? Oh, there's the digital me that we have to worry about, or what do you call it? The byte frequency.
Yeah, for the radian, I call it the byte. Yeah.
So like
the radian frequency, the 2 pi f, or the rise time of the signal.
Yeah, I guess so. So yeah, you can't say like, I remember I was saying like, what resistor would you put there instead of 43 ohms? The answer depends on what frequency you're talking about, I guess, because this whole thing changes.
Yeah. No, absolutely. Right. And so when we came up, for example, with driving DRAM arrays and using 22 ohms, it was a compromise between how fast could we go and how much spray we had. I used to actually, run over and, I didn't have any near field probes back then, but I had an antenna set up and I would look to see if I could see extra noise. Sometimes I couldn't, sometimes I could.
So this particular thing, it has an input resistance of maybe, I think we were saying is around 300 ohms or so. And I think if you look up, if you then say, oh, that's caused by input capacitance on that pin, and you reverse out the math and you say, what would the capacitance, or what would the capacitance of that pin be? I think we came out around a few puffs, maybe 3 puffs or so. 3 picofarads.
Yeah, the spec for a lot of TTL is 3 to 5 picofarad, and I usually attributed that to the packaging. I usually wrote off a couple puff just for the package, just for the pin going in through the epoxy and everything.
Oh, okay. So like the trace of the line probably has capacitance to just the stuff around it, I guess.
Everything, yeah.
Oh yeah, that packaging, I guess, is basically a dielectric, maybe. I don't know. I guess. Yeah.
So and nowadays at the frequencies we're working with BGA, and that'd be a great topic for Ben. Just the challenges of getting signals in and out, and not everybody's gotten it right. Not to disparage Xilinx, but I'll go ahead and do it because they pissed me off at one time.
They cut you deep.
They didn't. They could have told a friend of mine what was going on with the Spartan line, and they didn't. And they were having true problems at speed with the package layout, the inductance. Inductance resists a change of current. They had too much lead inductance getting to the right places at the right time, and then of course on the actual substrates, more decoupling and things. It didn't work. They had to relay out their pin layouts, and matter of fact, you can see some of that in Lee Ritchie's book. He shows like a bad BGA layout and a good BGA pin layout in there. Right the first time is his book.
Oh, okay. Yeah, I remember him talking about you need a lot of ground pins to do
in
things
the right
proper.
Places, and that was part of it. Yeah, in the right places to minimize and whatnot. And then you still have to get 582 signals out from the same area, so it's and these BGAs these days can pull tens of amps, right?
Oh,
so how do you get that kind of current into, think of it, if a part is 80 watts, we know Pentium processors are 80 watts, 100 watts. At 1 volt, that's 100 amps. That's 80 to 100 amps. So now we've got to worry about heavy DC getting there, in addition to all these signals getting in and out.
What's interesting about that Xilinx story is that, like, if they screw up and make a mistake, of course they have plenty of incentive to try to hide it or whatever.
Well, they
like,
hid it from a friend of mine for 3 months, where they
but,
kept telling them, "No, it's you. No, it's you. Hey, it was us."
but then,
And
but
they
we're
knew
talking
that.
about like things you can measure in math, and you're talking about electrical engineers who are going to figure it out in the end.
Eventually.
You can only hide this for so long, but yeah, you could trick someone for a few months, and yeah.
Right, and that was it. When he went faster, it would break. It was that simple,
It just seems like a unwise path to go down, to try to mess with an electrical engineer.
Engineers, yeah, yeah,
they're going to figure out what you're talking.
Yeah,
man.
absolutely. So, what else you got? You did some other explorations here of the high-speed digital design book.
Oh man. So let's see. I'm trying to remember if there's any other experiments I have lying around here. So what I would typically want to do is just every time I read one of those things that he has. Oh, the most recent one was like metastability. There's a thing in.
Oh yes, that was it. Do you
Okay.
have like your metastability stuff you had?
Oh,
What?
I could probably find the picture of it, so we could talk about what metastability is.
Yeah, find the picture if you could real quick. So basically, what I almost called you Ben. What Mike did
That would
was
be an honor. Yeah.
yeah. What Mike did was read about metastability and then set out to prove metastability exists. And now in my world, I had to learn the hard way metastability exists. I troubleshot somebody else's circuit, and they had put a capacitor on a clock line, made it slew way too long, and we got into metastability. But we get the same effect. What metastability is, if I have a clocking circuit and the data is still moving right when it's clocking, it looks like an asynchronous event. You propagate the unknown is how I talk about it, and we've talked about it on past shows. Great picture.
So I didn't understand. So so my understanding was probably I had a misapprehension of metastability until I read Howard Johnson's book, and he has like one little chapter where he like explains it in a way that spoke to me, and I was like, I finally get it now. And really, a lot of times I think you might hear people talk about like avoid being in that middle region, because you're basically dancing with metastability if you're in there. But Howard Johnson explained it as kind of like let's see if I could do this. Like basically you have a signal that's going to either go up or down based on where it started. And metastability is kind of like that idea. If you imagine a ball on a surface, right? And you put a ball right at the, like maybe you have like a peak of a surface,
right.
a mountain or whatever, and you balance that ball right at the top there. Well, the ball's going to go one way or the other in the end, because of some little gust of wind is going to blow the ball one way or the other. And metastability, at least one main effect of it is that, you found the Howard Johnson picture. The main effect is that if you get close to that point, once you kind of like, especially if you have a flip-flop or a latch, once it latches that point, and you pick your initial conditions basically, then you risk it taking an unbounded amount of time for it to finally go one way or the other. And your traces basically, it's not that you're seeing noise or anything weird. It's just that your traces are like sliding to the right as it finally takes longer and longer for the internal flip-flop mechanisms to pick which way it's going to go.
Right.
And
there are two sections in the flip-flop. There's a master and a slave that's there to try and stop this behavior. But if you screw up bad enough, it can propagate from the master section to the slave section if your clock rise time's too slow, or your setup time or hold time, people forget about hold time sometimes, doesn't meet the spec. It's still transitioning when the clock happens, and this uncertainty that I call it can make its way from the master section into the slave section. But then, as you say, it's bistable. It'll settle in one way or the other.
Yeah, so what you're seeing in this scope trace here is, like Bill said, the master half of the flip-flop is metastable at that point, and it stays metastable until it decides which way to go, and then the slave half of it sees that and it snaps one way or the other quickly. And what Bill is saying is, like, if that delay gets long enough, it can make it to the slave side, then you won't see that snap behavior. You'll see the slow exponential curve as it finally like drives up or down. And you just basically okay, so one thing for me is that this finally explained what was the big deal with setup and hold times.
Right,
Or
right.
like
You're still in the linear region when the clock happens, and that's an unknown.
basically, like if you read these specs, you're like, okay, set up and hold, I have to honor that, right? We all agree you better follow the rules. And the question is like, well, what if I don't? So what's going to happen? What's bad's going to happen? This is the bad thing that'll happen. If you don't set up and hold properly, you could end up in this metastable region, and your timings are just all off. Yeah.
Now, in DRAMs, for example, or other memory, if you let metastability in the door there, it can propagate around inside the chip, and even though you're doing a read cycle, you would think a read would never corrupt memory.
Yes.
But if you let this happen to your address drivers internally, and let's say multiple address drivers turn on, you end up with contention and everything else, and you can actually lose corrupt the contents of your memory by violating your setup and hold time, even on a read cycle. And once I had a DRAM designer tell me that, I was like, oh, now, I haven't had a DRAM problem I couldn't fix after talking to the DRAM designer himself.
So what I did,
yeah, that's a great picture you have. Yeah.
What I did to make this chart, if you look at Howard Johnson's book, he has a very clever circuit to try to make metastability occur more frequently. And he wrote this back in the early 90s, I guess. But what I did was I have a fancy signal generator that probably weren't available back then. And I basically just have the data and the clock offset from each other, because I have two signals come out of the signal generator, and I was able to tweak them, stick out my tongue and tweak it slightly until I got them like right at that point where you start to see this happening, So
you know how we did it in the old days? We'd lick our finger, put it on that thing to create a delay by pressing harder and harder. We get more and more capacitance as the area goes up. I've used my finger as a test probe more times than I can count, because we didn't have the kind of equipment in the old days that we do now.
Okay, yeah.
And you even see that on his drawings where he's got these point plots where this is multiple traces it took to create that. Even though yours is multiple traces, yours is filled it in and it'll look like lines.
Yep.
My gosh, we used to kill for the kind of scopes we have today back in the old days.
And if you look at the scope traces that I have, just to be clear, if you look at like the bottom trace and the top trace, they look very wavy. It doesn't look like nice square waves. That is simply because I was doing this on a breadboard, and I had like lines flying, trace, I had
so you sinned,
everywhere.
but you sinned.
Yeah, basically. So the noisiness that you're seeing, that's not the metastability. The metastability is those traces sliding to the right in the middle. Right. Yeah. So you can ignore all the other noise, yeah.
No, I like noise. If you're trying to demonstrate metastability, having some ground noise can only help, is the way I figure.
Yeah.
So, because it's about the imbalance of everything. It's about not minding your P's and Q's. And again, if this hazy part gets into, if something's being clocked during that haze, that next thing is going to be experiencing could experience metastability also.
Yeah, because then you're not doing the setup and holds for the next thing down the line.
That's right.
Yeah.
Right. And that's why I call propagation the unknown, or anytime it's in a linear region or it's violating the setup and hold times. That to me that's an X. It's not a high, it's not a low, it's an X. So when I say propagation of an unknown, I'm talking about propagating a not high or a not low. It's all that other garbage, regardless where it came from. Undershoot, overshoot, that's all unknown when it's not a high or a low.
So I have to do this. I think I'm just too, I don't know, I'm too speculative or whatever. I believe the stuff that I read in these books, but then I feel like I have to make it for myself. And then if you do it, if you make these circuits yourself, you just have a next level deeper understanding once you've built it for yourself and you see it,
Do you have any spare boards of this? You sent me one. Do you have any of these non-populated or anything?
Yeah, I got 5 of them, of course, because that's the minimum you get, right? Yeah,
right.
Got a whole bunch of them. Yeah.
So I not to kind of imply anything here, but if somebody were to ask you on Discord for one of the boards to experiment with, you would might have.
Yeah. So
you know what? Let me post the Discord invite while I'm at it.
Yeah. So these are fun experiments to do because you can if you get into making PCBs, you make these things, and then I have like an extra few lying around. So if anyone wants them,
right.
Just shoot you.
Oh, so I know what I was going to ask you. How'd you calculate your impedance, or did you? Because you said 6 mil on 2330. What do we have here for?
Oh, material? Okay. For this board, Yeah.
23 JLC 2313.
Yes.
My memory is 6 mil was not. It was closer to 5 mil ended up being 50 ohms on the 2313. How'd you calculate your impedance?
Okay, so this particular board has what's called coplanar waveguide, and
Right.
because it's got a I don't want to. I guess it's a ground plane on the top as well, right? So to answer your question, I used that Saturn PCB calculator, and I just
Saturn PCB.
yeah,
Okay.
I picked the coplanar waveguide choice in there and said, hey, tell me what does it need to be.
Now, have you thrown this on the TDR to see how good of impedance you got?
I did with some. Yeah. Okay. So. I
So
did not
for
with this
everybody,
board,
yeah.
Yeah.
Tell us about your TDR. What kind of TDR do you have?
Oh, I've got the same one you do, Bill.
Right. So tell us about it.
So it is basically it's an old Tektronix. Let's see, there it is over there. Let me get this thing out of the way. So basically, you can get this is the largest piece of equipment I own. That's like if you have test.
It's probably the loudest too.
Yeah, and it's the heaviest thing. Like once your test equipment weighs more than you have to stop.
Well, it's based on a CRT also. Probably the rest. Oh no, you do have an analog scope there. But I was going to say nowadays we're spoiled with LCD displays. Everything used to be CRT in the old days.
So since we have Alan online, there's like 3 Tektronixes in the display. So just to make Alan happy. But yeah.
But your one of your scopes got a virus, right?
Yes, Alan. This one here. Let me show you why.
Yeah.
Let me reboot this thing, and you'll see why I got a virus. Let me power it down. So while we're talking about the TDR, you can watch that thing boot. So
right.
So the TDR is basically a very fast sampling head, right? It's a sampling oscilloscope.
It's a pulse generator and a sampling
pulse generator,
head. Yes.
all built into the same thing. Yeah. So what you can do, at least I have, is you can like build. Oh, see, that's why it got a virus. You can see now.
It's Windows
Behold.
2000.
That was deemed a wise idea back then when they made the scope.
Well, I recommend you take a hot glue gun and fill the Ethernet connector on the back of it so that you don't have to worry about outside virus influences again.
Also, I have like the little thumb drives that I use to get screenshots off of it. I have to be careful. So
hot glue gun in the USB port too. You're done with screenshots. That's
okay.
my opinion.
Well, I've been careful. I have like a little special USB that you can lock. So it only, but if I ever flip it the wrong way at the wrong time, I could say goodbye to my scope.
Right. Alan said you can't blame him. You have to blame Microsoft.
Oh, this was probably before Alan was even at Tech. But yeah, it's Microsoft's fault too. Yeah.
Yeah, 21 years ago. Yeah. So, the real thing, the real problem, and it is a Microsoft problem, and submarines have this problem. At what point do you have to keep updating software that's, I don't want to say it's designed to be updated every 3 years, but boy, it sure seems like 5 years. Mm-hmm. You can't use Windows 7 on a government system currently, at least you're not supposed to. And how old's Windows 7? It's only 5 years old. There is no more support unless you pay outlandish support contracts for it.
For what it's worth, I think the Keysight multimeter is also running a variant of Windows called Windows CE.
CE? Okay.
So maybe it'll have the same problem at some point too. I mean,
Does it have an Ethernet port on it?
I don't think so, but it has a USB here to get screenshots off of it. So maybe one day I'll kill it with a virus. I don't know.
Right, because you probably can't change the boot characteristics. It might automatically auto run when you plug a USB key into it.
Yeah. Yeah, I know.
Wow. People are asking why Windows for oscilloscopes, and probably the answer is, well, they needed an operating system. And
it also, for what it's worth, it has Linux inside as well, I believe. Like there's the graphics or the trace capture card deep down in there, I think, is running a Linux, and then it's just the UI that's running. Like this part of the screen here is driven by Linux, evidently, and then the Chrome around it, like you can see, like that's a Windows. You probably can't see it from there, but it's all the UI is Windows, and if you look at their documentation, they're basically touting that like this makes it easy to do stuff, right? You can like interact with the scope, share files, get files off of it, run programs on your scope, but yeah. Here.
What's this? Somebody says, Bill says you're going to use Windows and you're going to like it. No, I'm saying that 21 years ago, Linux wasn't what it is today. And Linux gets viruses also. It's really a problem of there's incentivized people that want to break the stuff you own. And it's a constant battle to keep it up to date. And so equipment that's 20 years old, how are you going to keep it up to date? You know, you put hot glue in the Ethernet port. You know, that's my answer.
Yeah. You just stop messing with it. Yeah.
Right. Hey, so it's been an hour already. Can you believe that?
Oh, wow. Yeah. Awesome.
So, buggered our way through. So again, next week, Alan Wolke is joining us for, I always thought he was mispronouncing his own name there, so I apologize for that.
Alan Wolke?
Yeah. But I guess he would know how to say it. But he'll be joining us and showing, let's see what he just said something here, gives us the choice of running. Oh, look at that. One of the new techs has a choice between Linux or Windows 10. That's pretty interesting. Yeah, somebody disparaged Bill Gates right afterwards. So we're going to be showing spectrum analyzers that Alan has to show us. And we're going to be talking about the ISM band, the Industrial Scientific Medical Band. And I hope to see constellations and Bluetooth jumping in and out, and basically, Mike, some of the stuff you and me have been playing with, where you can see the WLAN getting in there, and then the Bluetooth getting in there, and all these different beaconings going on and stuff, and have somebody explain it.
I want something that can show a constellation diagram. Or something like that, you know.
I have now mine can't because I don't have the software enabled for it, but his does. So we get to see a constellation and talk about that. Because I'll tell you that it's actually math that goes into a constellation, but to me it was always art, right? Figuring out what worked under certain noisy conditions and bandwidth limitations, what gets you the best signal to error rate and signal noise and reduced bit error rates and stuff. So, excellent. Anything else you would add before we close here today?
I would just suggest trying these experiments yourself. These are, I don't know. That's a good way to learn, is just build this stuff and try it. And it's easy these days that you can like print a PCB for like whatever it is, $5. I don't know. I guess it's
well, the trick is to have it.
Or whatever.
Right. And some of the people in Discord, when we asked what CAD do you use, a not insignificant number of people use the CAD provided by the PC board house. So there's dedicated. You don't need to go and buy. You happen to have Proteus, which costs you how much? Whoops, I lost you there. There you're coming back. So a free alternative obviously is KiCad and go ahead. Yeah, we lost you there, Mike. So we'll probably just wrap up. Now we're getting the Skype beep.
Oh, okay.
Okay, you're back.
Maybe
I'm sorry
to end the show. Okay.
Yeah, that's basically it. We've run out of electrons, folks.
Yeah.
So, but I was going to say, what I was throwing out there was a plug for KiCad if you wanted a free version. I don't know how to say KiCad, but
KiCad.
KiCad, yeah. So, all right, everybody, we will see you next week, and stay tuned. We have a very special show next week. Not stay tuned, but be tuned in next week. So, all right, everybody. Hey, Mike, thanks for filling in, and you'll be watching next week, right?
Yes, definitely. Yeah.